Welcome to Topcast, and for my continuing series on the fabric of reality, we're up to Chapter 2, Shadows, for what I imagine will be a relatively short episode. And the reason for that I flagged in a previous episode because I've already completed approximately a 5-part series on the multiverse, which is essentially what this is about. This chapter is focused on quantum theory. As I've also said previously and in various other forums, this was the chapter that had the most profound impact on me when it came to reading the fabric of reality. And the reason for that, I suppose, is twofold. On the one hand, I was struggling when I first read this chapter to understand quantum theory. I was studying it at university in the undergraduate level, and we were working through problem sets and doing exercises as you do in university physics classes. And although I could mechanically work through how to get the answer, I didn't understand what I was doing. I didn't understand exactly what the Schrödinger wave equation, for example, was telling me about reality. I didn't understand how to interpret the experiments, one of which David is going to explain to us today, and which I'm going to go through again. So in this confusion, this haze of disillusionment, I suppose, with the way in which I was being presented quantum theory by both my lecturers at university and by other popularizers of science who'd written books on the subject, like Paul Davies, for example, who writes some very exciting and interesting books about, that touch upon at least, quantum theory. I never felt like I was getting an explanation that made any sense. And when I read the explanation here in Chapter 2, Shadows, it made sense. And so that was why it was so astonishing to me on the one hand, and why it had such a profound impact on me, because here finally, for the first time, I got it. I felt as if now I understood what quantum theory was an explanation of, what it was telling us about reality. That's on the one hand. On the other hand, it was the fact that what it was telling us about reality was so astonishing. I kind of knew that it had to be astonishing in some way, shape or form because I'd read various other so-called interpretations, and they were wacky to say the least. Things like the human mind or consciousness was somehow involved in fundamental physics. I didn't like this. It didn't ring true to me because I didn't think there could be a place, really, for something as emergent and complex and large as the human brain, giving rise to the mind, on fundamental particles. It evoked what Einstein called spooky action at a distance. I, like Einstein, not to put myself in the same category, but I rejected this idea. I regarded it as spooky, this idea that if you're observing something, then the experiment goes in one direction, and if you're not observing something, the experiment goes in a different direction. I felt either this was a prosaic claim about the way in which light interacted with matter, who cares, or it was a weird claim about if you passively think of something, then that can affect a physical system somewhere or other. Anyway, I wasn't buying it. I didn't understand it. But here we actually get the explanation. So I'm going to do an abridged reading today of the chapter and go through the double slit experiment, the way that David puts it in his words. And I've done this before, actually, in the Beginning of Infinity series, but we'll do it again here because this is the fabric of reality. So here we are, Chapter 2, Shadows, and David writes, "There is no more open door by which you can enter into the study of natural philosophy than by considering the physical phenomena of a candle." Michael Faraday, a course of 6 lectures on the chemical history of a candle. In his popular Royal Institution lectures on science, Michael Faraday used to urge his audiences to learn about the world by considering what happens when a candle burns. I am going to consider an electric torch or flashlight instead. This is quite fitting, for much of the technology of an electric torch is based on Faraday's discoveries. I am going to describe some experiments which demonstrate phenomena that are at the core of quantum physics. Experiments of this sort, with many variations and refinements, have been the bread and butter of quantum optics for many years. There is no controversy about the results, yet even now some of them are hard to believe. The basic experiments are remarkably austere. They require neither specialized scientific instruments, nor any great knowledge of mathematics or physics. Essentially, they involve nothing but casting shadows. But the patterns of light and shadow that an ordinary electric torch can cast are very strange. When considered carefully, they have extraordinary ramifications. Explaining them requires not just new physical laws, but a new level of description and explanation that goes beyond what was previously regarded as being the scope of science. But first, it reveals the existence of parallel universes. How can it? What conceivable pattern of shadows could have implications like that? Imagine an electric torch switched on in an otherwise dark room. Light emanates from the filament of the torch's bulb and fills out part of a cone. In order not to complicate the experiment with reflected light, the walls of the room should be totally absorbent, matte black. Alternatively, since we are only imagining these experiments, we could imagine a room of astronomical size, so there is no time for any light to reach the walls and return before the experiment is completed. Figure 2.1 illustrates the situation, but it is somewhat misleading. If we were observing the torch from the side, we should be able to see neither it nor, of course, its light. Invisibility is one of the more straightforward properties of light. We see light only if it enters our eyes, though we usually speak of seeing the object in our line of sight that last affected that light. Okay, pausing there, just my reflection on this. Yes, this can be sometimes surprising to people who hear it for the first time, that light is invisible. What that means is that if light is passing in that direction, let's say, and not entering your eye, then there's no way that you can possibly detect it. You can't see it, which is why the laser bolts in Star Wars should be invisible. Now, we don't know what these laser bolts, technically speaking, consist of, and Star Wars might very well be a magical universe separated from our own, operating via different physical laws. Indeed, the existence of the Force probably suggests that that is the case, but presuming that you could indeed have bullets made of light coming from stormtrooper guns, then you wouldn't be able to see them, unless, of course, they're not actually made of light, which is quite possible. After all, they're moving much, much slower than light. Indeed, they're moving much, much slower than typical bullets are, so Star Wars laser bolts aren't lasers. You can only see stuff that light reflects off. And when you see stuff, what you're seeing are the photons entering your eye. If a laser is shone from here to there, you don't see the laser beam. For example, here's my laser pointer. Here's me putting the laser pointer on. You can't see it. I can see the little dot over there. And if I put the laser behind me, I'm not sure if that'll show up on my screen or whatever, but here you can probably see it on my forehead there. Now, if I point it at you, then you can see it, right? So lasers, as they go from one place to another, you can't actually see the photons. So explain those pictures where you can see the laser light. Well, that's because you've got some sort of smoke or mist or something in the room and it's reflecting off the laser ray, beam, whatever you want to call it. The photons of light are crashing into matter particles of dust, usually of some kind or other. So the other thing to say about light, especially light such as comes out of a normal torch, and this is something we all have experience with, is that if you are close to the source of light, if you're close to where the torch is, then the torch is bright, and the further you move away from the torch, the more dim it becomes. Not surprising. And the reason is that the light is spreading out over an ever greater area. And so it's getting spread more and more thinly, like butter being spread over more bread. Let me go back to the book at this point. And David writes, can light really be spread more and more thinly without limit? The answer is no. At a distance of approximately 10,000 kilometres from the torch, its light would be too faint for the human eye to detect, and the observer would see nothing. That is, a human observer would see nothing. But what about an animal with more sensitive vision? Frogs' eyes are several times more sensitive than human eyes, just enough to make a significant difference in this experiment. If the observer were a frog, and it kept moving further away from the torch, the moment at which it entirely lost sight of the torch would never come. Instead, the frog would see the torch light begin to flicker. The flickers would come at irregular intervals that would become longer as the frog moved further away. But the brightness of the individual flickers would not diminish. At a distance of 100 million kilometres from the torch, the frog would see on average only one flicker of light per day, but that flicker would be as bright as any that it observed at any other distance. Frogs cannot tell us what they see, so in real experiments we use photomultipliers, light detectors which are even more sensitive than frogs' eyes, and we thin out the light by passing it through dark filters rather than by observing it from 100 million kilometres away. Okay, and then David compares light to gold. you can't thin out light infinitely. There comes a point at which the light begins to flicker. In a similar way, gold isn't infinitely malleable. Now, I've used this example myself, and it's an interesting psychological trick that is played on one's mind. I actually thought this analogy was something that I sort of came up with, but no, here it is. Gold is mentioned here in the Fabric of Reality, so I have absorbed it there, and only just reading it here again now do I realize that, the reason why I keep using gold as my go-to example of what stuff is quantized is because it's here in the Fabric of Reality. So if you hammer out a metal, the degree to which you can hammer it out, or the ease with which you can hammer it out, is known as the malleability of that material. So gold is extremely malleable. You can spread it so thin, of course, that you can get that gold leaf stuff that is extremely thin indeed. But you can't make gold infinitely thin, because you eventually get down to the gold atom. And once you get down to the gold atom, if you were to try and break that down still further, you would no longer have gold. You'd have half of a gold atom, which is no longer gold. So as David writes, and I'll pick up from where he talks about this, he writes, "So the only way in which one can make a one atom thick gold sheet even thinner is to space the atoms further apart, with empty space between them. When they are sufficiently far apart, it becomes misleading to think of them as forming a continuous sheet. For example, if each gold atom were on average several centimetres from its nearest neighbour, one might pass one's hand through the sheet without touching any gold at all. Similarly, there is an ultimate lump or atom of light, a photon. Each flicker seen by the frog is caused by a photon striking the retina of its eye." Pausing there, my reflection. So, what David's talking about here is, of course, quantization. This concept that there is the smallest possible unit of stuff. In the case of gold, the smallest possible unit of stuff is the gold atom. In the case of light, it is the photon of light, the smallest particle of light. In the case of electricity, the smallest possible particle is the electron. In the case of water, it's the water molecule. And repeat for all stuff that's made out of matter, anything that appears in the so-called standard model of particle physics. All the stuff that you can see around you is going to have a smallest possible unit of stuff that makes it up. When I say everything, of course, I mean the everything that's made out of pure substances. You, of course, see mixtures around you. So if you have, in the simplest case, salt water, then the smallest possible unit of salt water is not a unit of salt water. The smallest possible unit are two discrete things, one of which is called the salt lattice. Well, really, it's made of two ions, the sodium and the chloride, which are bonded together via electrostatic forces, and the water molecule. And so these two things constitute the units out of which the mixture, salt water, is made. So a lot of the things you see in your environment, of course, are mixtures, including human beings, for example, which are made up of lots of pure substances, each of which have a smallest possible unit. So pretty much everything is quantized. What doesn't appear to be quantized, or what we don't know about the quantization of, are things like gravity. It has been suggested that the standard model should contain a graviton. I don't know why, but this is just what people who want to quantize space-time or quantize gravity talk about. They talk about a particle gravity. Never been observed, and doesn't appear to explain anything, because we have an explanation of gravity, which is in terms of space-time, which is continuously divisible. Under that theory, under general relativity, we don't have a smallest unit of time or a smallest unit of space or a smallest unit of space-time, etc. But this idea of quantization in physics within the realm of quantum physics is the thing that gives quantum theory its name. There is a quanta, a smallest particle of something. Okay, so I'm skipping, as I say, a number of pages there, and I'm picking up where David says, "I have made an assumption about light, namely that it travels only in straight lines. From everyday experience we know that it does, for we cannot see around corners. But careful experiments show that light does not always travel in straight lines. Under some circumstances, it bends. This is hard to demonstrate with a torch alone, just because it is difficult to make very tiny filaments and very black surfaces. These practical difficulties mask the limits that fundamental physics imposes on the sharpness of shadows. Fortunately, the bending of light can also be demonstrated in a different way. Suppose that the light of a torch passes through two successive small holes, in otherwise opaque screens, as shown in figure 2.4, and that the emerging light falls on the third screen beyond. Our question now is this: if the experiment is repeated with ever smaller holes and with ever greater separation between the first and second screens, can one bring the umbra, the region of total darkness, ever closer without limit to the straight line through the centres of the two holes? Can the illuminated region between the second and third screens be confined to an arbitrarily narrow cone? In Goldsmith's terminology, we are now asking something like, how ductile is light? How fine a thread can it be drawn into? It turns out light is not as ductile as gold. Long before the holes get as small as a 10,000th of a millimetre, in fact, even with holes as large as a millimetre or so in diameter, the light begins noticeably to rebel. Instead of passing through the holes in straight lines, it refuses to be confined and spreads out after each hole, and as it spreads, it frays. The smaller the hole, the more the light spreads out from its straight line path. Intricate patterns of light and dark shadow appear. We no longer see simply a bright region and a dark region on the third screen with a penumbra in between, but instead concentric rings of varying thickness and brightness. There is also colour, because white light consists of a mixture of photons of various colours, and each colour spreads and frays in a slightly different pattern. Figure 2.5 shows a typical pattern that might be formed on the third screen by white light that has passed through holes in the first two screens. Remember, there is nothing happening here but the casting of a shadow. Figure 2.5 is just the shadow that would be cast by the second screen in figure 2.4. If light travelled only in straight lines, there would be only a tiny white dot, much smaller than the central bright spot in figure 2.5, surrounded by a very narrow penumbra. Outside that, there would be pure umbra, total darkness. Okay, pausing there, my reflection, just skipping a little bit more. At this point, nothing to a science student, in particular a physics student, as I was 20 plus years ago, was particularly surprising in what David had said. It was a little bit idiosyncratic, I thought, perhaps, that he was invoking frogs and torches, and I thought it was a nice harking back to the fact that, yes, Michael Faraday would explain stuff through contemplation of the operation of how a candle produced light, and so that was lovely. But so far, nothing particularly surprising. Pretty much run-of-the-mill science, and the same kind of way in which things would be explained in a clear way with analogies, such as the analogy of light being quantized to gold being quantized. But now we're about to get into the part where, as I've said before, the sense of vertigo comes in. For anyone who hasn't heard this description of the experiment before, much less the explanation which is to come. The description of the experiment, including the result, is rather strange. The first part, if you've even done high school physics, won't seem to be that mysterious. It is the double slit experiment. But how it works with single photons, well, that is the challenging part for us. So let's dive straight into it. David writes, Figure 2.6 shows at roughly its actual size a part of the pattern of shadows cast 3 meters from a pair of straight parallel slits in an otherwise opaque barrier. The slits are 1/5 of a millimeter apart and illuminated by a parallel-sided beam of pure red light from a laser on the other side of the barrier. Why laser light and not torchlight? Only because the precise shape of a shadow also depends on the colour of the light in which it is cast. White light, as produced by a torch, contains a mixture of all visible colours, so it can cast shadows with multicoloured fringes. Therefore, in experiments about the precise shapes of shadows, we are better off using a light of a single colour. We could put a coloured filter, such as a pane of coloured glass, over the front of the torch so that only light of that colour would get through. That would help, but filters are not all that discriminating. A better method is to use laser light, for lasers can be tuned very accurately to emit light of whatever colour we choose with almost no other colour present. If light travelled in straight lines, the pattern in figure 2.6 would consist simply of a pair of bright bands 1/5 of a millimetre apart, too close to distinguish on this scale, with sharp edges and with the rest of the screen in shadow. But in reality, The light bends in such a way as to make many bright bands and dark bands and no sharp edges at all. If the slits are moved sideways, so long as they remain within the laser beam, the pattern also moves by the same amount. In this respect, it behaves exactly like an ordinary, large-scale shadow. Now, what sort of shadow is cast if we cut a second identical pair of slits in the barrier interleaved with the existing pair so that we have 4 slits at intervals of 1/10 of a millimetre? We might expect the pattern to look almost exactly like figure 2.6. After all, the first pair of slits by itself casts the shadow in figure 2.6, and as I have just said, the second pair by itself would cast the same pattern, shifted about 1/10 of a millimetre to the side in almost the same place. We even know that light beams normally pass through each other unaffected, so the 2 pairs of slits together should give essentially the same pattern again, though twice as bright and slightly more blurred. In reality though, what happens is nothing like that. The real shadow of a barrier with 4 straight parallel slits is shown in figure 2.7a. For comparison, I have repeated below it the illustration of the 2-slit pattern, figure 2.7b. Clearly, the 4-slit shadow is not a combination of 2 slightly displaced 2-slit shadows, but has a new and more complicated pattern. In this pattern, there are places such as the point marked X, which are dark on the 4-slit pattern, but bright on the 2-slit pattern. These places were bright when there were 2 slits in the barrier, but went dark when we cut a second pair of slits for the light to pass through. Opening those slits has interfered with the light that was previously arriving at X. So adding 2 more light sources darkens the point at X. Removing them illuminates it again. Pausing there, just my reflection. Now, at this point, I still recall, to some extent, the excitement of reading that. Even though I didn't know the explanation yet, I'd read that sort of thing before, but probably not quite as well explained exactly what the problem was. But this idea that if you open up more places for the light to come through, you actually decrease the amount of light on the screen. There's more shadows, even though you've got more light sources. You had previously 2 places for the light to come through, and you had a certain pattern of light and dark, and then you open up more places for the light to go through, more gaps, more slits, and you actually decrease the amount of light. You actually increase the number of shadows. This seems bizarre. It's like opening up more places for the light to get through darkens the screen. So this is really mysterious. And I don't know exactly what my psychology was back at the time of reading this, but I guess it might have been something like, I'm about to be given another confusing account of what's going on here. I'm not going to understand this. I've read about this before. I've even conducted this experiment myself before, and I've had lecturers tell me about, the results of the experiment and what it could mean, and I haven't understood anything about what's going on. So I guess my hopes were pretty low for being given a realistic account, a clear account, a logical account that I would be able to actually explain to other people. After all, that's a measure of whether or not you understand something. If you can actually explain it to someone else such that they then walk away nodding their head and going, oh, now I also get it, then that means to some extent that you understand it. At the very least, you've convinced yourself you understand it, even if you might have some misconceptions. Okay, so backtracking a little bit and reading on. David wrote, "These places were bright when there were 2 slits in the barrier, but went dark when we cut a second pair of slits for the light to pass through. Opening those slits has interfered with the light that was previously arriving at X. So adding 2 more light sources darkens the point at X. Removing them illuminates it again. How? One might imagine 2 photons heading towards X and bouncing off each other, like billiard balls. Either photon alone would have hit X, but the 2 together interfere with each other so that they both end up elsewhere. I shall show in a moment that this explanation cannot be true. Nevertheless, the basic idea of it is inescapable. Something must be coming through that second pair of slits to prevent the light from the first pair from reaching X. But what? We can find out with the help of some further experiments. First, the 4-slit pattern of figure 2.7a appears only if all 4 slits are illuminated by the laser beam. If only 2 of them are illuminated, a 2-slit pattern appears. If 3 are illuminated, a 3-slit pattern appears, which looks different again. So whatever causes the interference is in the light beam. The 2-slit pattern also reappears if two of the slits are filled by anything opaque, but not if they are filled by anything transparent. In other words, the interfering entity is obstructed by anything that obstructs light, even something as insubstantial as fog. But it can penetrate anything that allows light to pass, even something as impenetrable to matter as diamond. If complicated systems of mirrors and lenses are placed anywhere in the apparatus, so long as light can travel from each slit to a particular point on the screen, what will be observed at that point will be part of a 4-slit pattern. If light from only 2 slits can reach a particular point, part of a 2-slit pattern will be observed there, and so on. So, whatever causes interference behaves like light. Just pausing there. What we mean by interference is something affecting that light that would have struck X, but which didn't. So remember, in figure B, we've got the pattern that happens, that occurs with 2 slits. And that bit that's light then goes dark when you add 2 more slits, additional places for the light to come through. So something's interfering with light that otherwise would have hit X in picture B. Now those photons that were heading towards point X, but which don't make it to point X, in figure A, when you've got those 2 extra slits, has been interfered with. Something's interfered with it. That's literally the word. So there's some reason why it hasn't gotten there when it would have got there. Okay, just going back to the book. Whatever causes interference behaves like light. It is found everywhere in the light beam and nowhere outside it. It is reflected, transmitted, or blocked by whatever reflects, transmits, or blocks light. You may be wondering why I'm labouring this point. Surely it is obvious that it is light. That is, what interferes with photons from each slit is photons from the other slits. But you may be inclined to doubt the obvious after the next experiment, the denouement of the series. What should we expect to happen when these experiments are performed with only 1 photon at a time? For instance, suppose that our torch is moved so far away that only 1 photon per day is falling on the screen. What will our frog observing from the screen see? If it is true that what interferes with each photon is other photons, then shouldn't the interference be lessened when the photons are very sparse? Should it not cease altogether when there is only 1 photon passing through the apparatus at any one time? We might still expect penumbras, since a photon might be capable of changing course when passing through a slit, perhaps by striking a glancing blow at the edge. But what we surely could not observe is any place on the screen, such as X, that receives photons when 2 slits are open, but which goes dark when 2 more are opened. Yet that is exactly what we do observe. However sparse the photons are, the shadow pattern remains the same. Even when the experiment is done, 1 photon at a time, none of them is ever observed to arrive at X when all 4 slits are open. Yet we need only close 2 slits for the flickering at X to resume. Could it be that the photon splits into fragments, which, after passing through the slits, change course and recombine? We can rule that possibility out too if again we fire 1 photon through the apparatus but use 4 detectors, 1 at each slit. Then at most 1 of them ever registers anything. Since in such an experiment we never observe 2 of the detectors going off at once, we can tell that the entities that they detect are not splitting up. So if the photons do not split into fragments and are not being deflected by other photons, what does deflect them? When a single photon at a time is passing through the apparatus, what can be coming through the other slits to interfere with it? Let us take stock. We have found that when 1 photon passes through the apparatus, it passes through 1 of the slits, and then something interferes with it, deflecting it in such a way that depends on what other slits are open. The interfering entities have passed through some of the other slits. The interfering entities behave exactly like photons, except that they cannot be seen. Pausing there, just my reflection, just a psychological reflection. So I think at this point, this is where the sense of vertigo really begins to happen. It's you're recognizing that David is offering for you, served up on a platter, the explanation. There are photons there that you can't see. Now, at this point, you don't understand the full explanation, but you're getting a hint of it. So everything can be understood at this point. Everything is logical, realistic. It makes sense. You're not having the wool pulled over your eyes. At no point, at least for me, do I have questions and go, but wait, what about? Because he's answering any of the objections I might have raised. If you have any objections throughout this, please write a question in the comments, because I like to talk about this stuff. It's very interesting to try and clarify if you're not too sure. Let's keep going. David writes, I shall now start calling the interfering entities photons. That is what they are, though for the moment it does appear that photons come in two sorts, which I shall temporarily call tangible photons and shadow photons. Tangible photons are the ones we can see or detect with instruments, whereas the shadow photons are intangible, invisible, detectable only indirectly through their interference effects on the tangible photons. Later, we shall see that there is no intrinsic difference between the tangible and shadow photons. Each photon is tangible in one universe and intangible in all other parallel universes. But I anticipate what we have inferred so far is only that each tangible photon has an accompanying retinue of shadow photons, and that when a photon passes through one of our 4 slits, some shadow photons pass through the other 3 slits. Since different interference patterns appear when we cut slits at the other places in the screen, provided that they are within the beam, shadow photons must be arriving all over the illuminated part of the screen whenever a tangible photon arrives. Therefore, there are many more shadow photons than tangible ones. How many? Experiments cannot put an upper bound on the number, but they do set a rough lower bound. In a laboratory, the largest area that we could conveniently illuminate with a laser might be about a square metre, and the smallest manageable size for the holes might be about 1/1000th of a millimetre. So there are about 1 trillion possible hole locations on the screen. Therefore, there must be at least 1 trillion shadow photons accompanying each tangible one. Thus we have inferred the existence of a seething, prodigiously complicated, hidden world of shadow photons. They travel at the speed of light, bounce off mirrors, are refracted by lenses, and are stopped by opaque barriers or filters of the wrong colour. Yet they do not trigger even the most sensitive detectors. The only thing in the universe that a shadow photon can be observed to affect is the tangible photon that it accompanies. That is the phenomena of interference. Well, pausing there. So at this point, I think I understood interference, and you should understand interference as well. Interference is these photons that you see physically colliding with these photons that cannot be seen. These photons that cannot be seen push aside the photons that you can see, because if they weren't there, then the photon would have just continued off through that double slit and landed in one of 2 places behind those 2 slits. That's the single photon version of reality, the classical universe version of reality. But that's not what we're in. We're in a multiverse. Back to the book. We're almost there at where we have to accept the explanation of the multiverse. David writes, shadow photons would go entirely unnoticed if it were not for this phenomena and the strange patterns of shadows by which we observe it. Interference is not a special property of photons alone. Quantum theory predicts and experiment confirms that it occurs for every sort of particle. So there must be hosts of shadow neutrons accompanying every tangible neutron, hosts of shadow electrons accompanying every electron, and so on. Each of these shadow particles is detectable only indirectly through its interference with the motion of its tangible counterparts. Pausing there. Okay, so at this point I think I accepted the multiverse account, because I knew about doing the twin slit experiment with electrons. In fact, I'd read about it being done with oxygen atoms. So it was clear to me at this time that, well, not only do you have this retinue of photons following around every photon you can see, you have a retinue of electrons following every electron that you can detect, and oxygen atoms, and therefore you just conclude that, well, every single particle of matter has a retinue of unseen counterparts. So that's it. We live in a multiverse. We live in a universe, a reality, where much of it is unseen. Which again, it's an astonishing fact, but it's also consistent with the history of ideas, of the universe just getting larger and expanding beyond what we can see. The seen, in terms of the unseen. Indeed, as David says, going back to the book, it follows that reality is a much bigger thing than it seems, and most of it is invisible. The objects and events that we and our instruments can directly observe are the merest tip of the iceberg. Now, tangible particles have a property that entitles us to call them collectively a universe. This is simply the defining property of being tangible, that is, of interacting with each other and hence of being directly detectable by instruments and sense organs made of other tangible particles. Because of the phenomena of interference, they are not wholly partitioned off from the rest of reality, that is, from the shadow particles. If they were, we should never have discovered that there is more to reality than tangible particles. But, to a good approximation, they do resemble the universe that we see around us in everyday life and the universe referred to in classical pre-quantum physics. For similar reasons, we might think of calling the shadow particles collectively a parallel universe, for they too are affected by tangible particles only through interference phenomena. But we can do better than that, for it turns out that shadow particles are partitioned among themselves in exactly the same way as the universe of tangible particles is partitioned from them. In other words, they do not form a single homogeneous parallel universe, vastly larger than the tangible one, but rather a huge number of parallel universes, each similar in composition to the tangible one, and each obeying the same laws of physics, but differing in that the particles are in different positions in each universe. Okay, just pausing there. And this is where it helped me understand the Schrödinger wave equation, which I'd been learning about. Because the Schrödinger wave equation gives you the distribution of all the positions that a particle can have. But you only ever observe one. And previously I'd of course been taught that, well, when you observe, this causes the collapse of the wave function. And the wave function is the thing given by the Schrödinger wave equation. And you make an observation and then you find that all of the different possibilities collapse into the one that you observe. All the others disappear. Which makes you think, why does the equation describe all of these other possible positions if only one of them really exists? What is going on there? And usually you're given the non-explanation that, well, this is just the formalism, this just helps you to predict the outcome of experiments, don't worry, it doesn't really mean anything in actual reality, there's no point asking about actual reality. What this says here is that in fact the Schrödinger wave equation, the wave function, is telling you that all these particles really do exist before and after, before, during and after an experiment is conducted. They really do exist. When you make an observation, you find out in which universe you are, in which universe you occupy. You occupy this one or you occupy that one. But all the others absolutely exist. And they continue to exist. They evolve over time. They change over time. The distribution of particles changes over time, but they all exist. Okay, I'm skipping a part there where David talks about terminology, this idea of the universe versus multiverse. And he writes, I'll just go to the bit where he explains the distinction. Quote, "A new word, multiverse, has been coined to denote physical reality as a whole. Single particle interference experiments such as I have been describing show us that the multiverse exists and it contains many counterparts of each particle in the tangible universe. To reach the further conclusion that the multiverse is roughly partitioned into parallel universes, we must consider interference phenomena involving more than one tangible photon. The simplest way of doing this is to ask, by the way of a thought experiment, what must be happening at the microscopic level when shadow photons strike an opaque object. They are stopped, of course. We know that because the interference ceases when an opaque barrier is placed in the paths of the shadow photons. But why? What stops them? We can rule out the straightforward answer that they are absorbed like tangible photons would be by the tangible atoms in the barrier. For one thing, we know that shadow photons do not interact with tangible atoms. For another, we can verify by measuring the atoms in the barrier, or more precisely, by replacing the barrier with a detector, that they neither absorb energy nor change their state in any way unless they are struck by tangible photons. Shadow photons have no effect. To put that another way, shadow photons and tangible photons are affected in identical ways when they reach a given barrier, but the barrier itself is not identically affected by the two types of photon." Pausing there. Okay, in other words, or in my words, if you're shining a torch at the wall, we know already, given David's explanation, that coming out of that torch are the photons you can see, and lots and lots. I would say the more modern understanding of quantum theory is uncountably infinite fungible instances of these other photons are also coming out of the torch. But when it hits a wall, an opaque barrier, the opaque barrier that you can see is only absorbing the photons that you can see. So how are all the other shadow photons being absorbed? Well, only because there must be shadow barriers there as well. There's a shadow wall there. However many shadow photons there are, that's how many shadow barriers there are, absorbing the photons, which leads you inexorably to the idea that everywhere there's matter, there are uncountably infinite copies of that matter existing, in a sense, in the same place at the same time. But I'd refer you to the book if you need more about this. Chapter 2 is certainly worth reading. And I'll just read the final part of the chapter. I've skipped a fair bit, and I'm ignoring stuff that David says there about instrumentalism because I've concentrated on that before in various episodes. So just the last part of this chapter, and David writes, "So far I have been using temporary terminology which suggests that one of the many parallel universes differs from the others by being tangible. It is time to sever that last link with the classical single universe conception of reality. Let us go back to our frog. We have seen that the story of the frog that stares at the distant torch for days at a time, waiting for the flicker that comes on average once a day, is not the whole story, because there must also be shadow frogs in shadow universes that coexist with the tangible one, also waiting for photons. Suppose that our frog is trained to jump when it sees a flicker. At the beginning of the experiment, the tangible frog will have a large set of shadow counterparts, all initially alike, but shortly afterwards they will no longer all be alike. Any particular one of them is unlikely to see a photon immediately." Pausing there. So all of these frogs that are alike beforehand, fungible instances? Indeed. So the beginning of infinity sharpens this notion up with new terminology, but it's the same idea. Back to the book. David writes, "Any particular one of them, the frogs, is unlikely to see a photon immediately, but what is a rare event in any one universe is a common event in the multiverse as a whole. At any instance, somewhere in the multiverse, there are a few instances in which one of the photons is currently striking the retina of the frog in that universe, and the frog jumps. Why exactly does it jump? Because within its universe, it obeys the same laws of physics as tangible frogs do, and its shadow retina has been struck by a shadow photon belonging to that universe. One of the light-sensitive shadow molecules in the shadow retina has responded by undergoing complex chemical changes to which the shadow frog's optic nerve has in turn responded. Shadow optic nerve. It has transmitted a message to the frog's shadow brain, and the frog has consequently experienced the sensation of seeing a flicker. Or should I say, the shadow sensation of seeing a flicker? Surely not. If shadow observers, be they frogs or people, are real, then the sensations must be real too. When they observe what we might call a shadow object, they observe that it is tangible. They observe this by the same means and according to the same definition as we apply when we say that the universe we observe is tangible. Tangibility is relative to a given observer. So objectively, there are not two kinds of photons, tangible and shadow, nor two kinds of frog, nor two kinds of universe, one tangible and the rest shadow. There is nothing in the description I have given of the formation of shadows or any of the related phenomena that distinguishes between tangible and shadow objects, apart from the mere assertion that one of the copies is tangible. When I introduce tangible and shadow photons, I apparently distinguish them by saying that we can see the former but not the latter. But who are we? While I was writing that, hosts of shadow Davids were writing it too. They drew a distinction between tangible and shadow photons, but the photons they called shadow included the ones I called tangible, and the photons they called tangible are among those I called shadow. Not only do none of the copies of an object have any privileged position in the explanation of shadows that I have just outlined, neither do they have a privileged position in the full mathematical explanation provided by quantum theory. I may feel subjectively that I am distinguished among the copies as the tangible one because I can directly perceive myself and not the others, but I must come to terms with the fact that all the others feel the same about themselves. Many of those Davids are at this moment writing these very words. Some are putting it better. Others have gone for a cup of tea. And there we end it. And that, as I say, is the most affecting, for me personally, of the chapters in the Fabric of Reality, because it explains what's going on in this double slit experiment. And once you understand that, coupled with this concept of quantization in quantum theory, you've gone a long way to understanding quantum theory. Maybe not the mathematical formalism, but who cares about that unless you want to be a professional? If you want to understand reality, the best that everyone who works in physics understands reality, then after reading Shadows, you will have a very good understanding. In fact, you might understand it better than some physicists, in fact, physicists who deny this way of explaining what we see in terms of the unseen. For more on this, find my multiverse series on YouTube. And until next time, bye-bye.